First things first, give a big shout out and thank you to Michelle Kramer sending this lovely copper to the rim face mask out to Singapore, all the way from the States. Much appreciated. Thank you, Michelle. Lovely to get a little bit of fan mail. Thank you. Okay, we're going to work with WebMO today, and we're going to look at how to accurately work out the bond angle of a molecule of your choosing. So anything you wish to build, you can build in here. If you've not seen the previous videos, the logon is guest and the password is guest, and you drop into this screen, hit the new job in the top left, create new job, and you land to the molecule building screen. Okay, wherever you click, a carbon atom will appear. You can drag and drop, and put a single bond in between two neighbouring carbon atoms. That's better, Mr. Mitchley. You can do it twice and you will get a double bond. Just be careful on where you're clicking and where you're dropping. You will get an extra atom, as you just saw. You can clean up very easily and just add hydrogens. There are my hydrogens. Hopefully, if I use my spinny tool, which is this one here, third one down, then I can spin this around and I can see along the molecule. Clearly, this is not the correct structure just yet. So what do we need to do? Clean up comprehensive mechanics, and now we're looking a lot more like what we'd expect it to, how we'd expect it to appear. So we can spin this around in space, which is beautiful. Obviously, we've made a molecule of propene here. We can add the molecular orbitals around and see where the electron density is. It's pretty flash. I like that one. We can also clean up either idealized, which is how we'd expect it from a textbook, or mechanics, which looks pretty much identical. I'm not sure what the difference is between those two different things, but you need to do either of them, so it needs to be cleaned up once you've built it. Okay, what have I learnt since the last video? I've learnt this, that it matters which order you click the atoms in if you want to harvest such information as the bond angle. So here's my carbon, I hit my carbon. This is sp2 hybridized. We know it is because there are 3 electron domains, 1, 2, 3, 2 hydrogens, and then the double bond composed of a pi and a sigma bond to the adjacent carbon. I then hit the second carbon, I get the bond length, which is 1.34 angstroms for a double bond. I unclick those because if I want to have a look at the bond length of my single bond, which is 1.505 angstroms, it matters which order I click them in. So depending on which one you want to select, always deselect where you want to begin, and then start. If that's carbon atom number 1, that's carbon atom number 2, and we get 1.34 angstroms, which is correct. You may be looking at different substituents on the effects on the bond length or in the bond angle, which is the purpose of this video we'll come to shortly. And that's how you do it. Just be very, very careful. Also be careful if you start clicking these outer hydrogens and you're going for the bond length there, okay, then the bond angle. Okay, that's actually worked. Sometimes it doesn't work. Just be careful. It's easy to click the wrong atom is the moral of the story, which I'm trying to tell you now. Okay, so we've built our molecule. We can build any molecule we want with the periodic table up here. We can do nice things like we can look at the electrostatic potential, which is lovely, and you get a beautiful textbook representation of propene here. We can see the pi electron density massively more prominent, profound, enhanced in comparison to the sigma electron density on the opposite end of the molecule. But we don't want to do that today. What we want to do is have a look at how we can actually get different data, particularly bond angle, from this software suite, which is WebMO, or WebMO as we like to call it. Okay, we're going to be looking at different cyclical structures, and we're going to have a look. Let's build some cyclopropane here. Drag and drop, calculate. I don't want to do that. I want to generate. I want to add hydrogens. Where I want to do, I want to complete. There we go. So complete, idealized, or comprehensive mechanics. Doesn't matter which one, they both work. Give that a spin around, that's all good. What would we expect? We would expect this to have a bond length. Was it 1.54 for a single? Oh, it's gone down, 1.431. So it's been compressed. What we can also do, just as a little aside as I'm thinking, we can also adjust the bond length. So we can see now it's 1.431. And we can have a look and we can do what's the strain energy. And here it's 161. Let's just remember 161 kilocalories per mole. Let's remember 161. Remember 161. Do that for me. Thank you very much. So what I can do, I can click those. Bond length 1.431. I can adjust the bond length. Let's take it to 1. Okay. Oh, we shrunk it. Okay. Now let's have a look at the strain energy. It's now 391 kilocalories per mole. Well, why would I want to do that? Well, first of all, it's quite fun to do, to see what we can do with the energy. But also, you can change the bond length to any length that you want it to be. You could take it, let's take it to 20 angstrom. I think it's going to break at that point. Look at that now. Wowzers, it's not even on the screen anymore. Okay, and if I calculate the strain energy of that one, oh my life, look at that. It's absolutely enormous. So what you can do is you can change the bond to very short, take it to very long, and find out you're building like a Morse curve. If you know what that is, have a look it up and see what you find. So I said we're going to do bond angle. What we're going to do is this. I built a little sheet here, which I will link under the video. I'm looking at cyclic structures, cyclic alkanes, so cyclopropane, butane, pentane, hexane. I started with heptane. I ran out of time. Family called. The data that I'm going to be gathering is the bond angle. So here we can see the bond angle. Butane around about 90, 88. Pentane 105. Hexane 110. Heptane 112. We'd expect that to carry on in that trend. We all understand bond angle. We've done that in VESPR or VSEPR theory in class. That's fine. Bond stretch, angle bend, stretch bend, torsional force, and van der Waals, giving us the total energy for the molecule, we might not know so much. Okay, so all these are calculations using Newtonian mechanics to work out the total energy of the molecule. So when I'm looking at bond stretch, it's the same bond stretch, and it's the same angle bend and stretch bend and torsional force as we kind of approximate to infrared spectroscopy and the bending and stretching within a molecule as it's vibrating around above absolute zero, any temperature above absolute zero. The van der Waals forces, I'll explain those shortly, giving the total energy of the molecule. Now what can we see? Bond angle, we understand, is getting bigger, okay. Bond stretch, whatever that means, 0.8 to 0.3 to 3.3, so it's gone high, low, bit up again. The angle bend, don't forget, this is the angle bend energy. It's not an angle in terms of degrees, it's the energy of that bend, and this is in kilocalories per mole, and 1 kilocalorie per mole is 4.184 kilojoules per mole, so we can do a calculation there. There's some data processing, that's great. Angle bend 22, 0.3, oh, there's a nice trend. Stretch bend 0.9, 0.9, 0.8 going down, linear, beautiful. 6.7, 6.32 going down, so now this one's going up. Van der Waals force is going up with increasing molecular mass. Well, this is good, right? So we're already starting to see some trends, and there's some very easy data that we can get. This total energy here, this is the sum of all of these energies. Okay, so let's get that here. So this is summed by just adding these up and giving the total energy. Don't forget, this is the energy from the Newtonian mechanical calculations, not from any additions from the molecular orbitals and the spin-spin contributions, which we shall come to shortly. So let's head back to WebMO. We want to build cyclopropane. So 1, 2, 3. I'm going to put these in. Can I just generate bonds? I think I can, can't I? Look at that. No, don't do that. Let's do it manually. Let's do it the old way. So here is my cyclopropane. What do I need to do next? I need to clean up. Comprehensive mechanics, that's good. Check that I've got 2 hydrogens per carbon. I have. I've not adjusted the bond length. I've not adjusted the angle. You can adjust the bond angle as well, actually. I'll give you a quick show of that one. I have been playing with this quite a lot, so hopefully I do feel at least a little bit more confident than the last ones that I did. So let's make the bond angle 60 degrees. Adjust the bond angle. Let's be hilarious. Let's make it 90 degrees. Is that even possible? I'm not sure it's done that. I'm not sure it's done that. But then you can calculate, you can look at the strain energy. That's going to be huge, isn't it? 437 kilocalories per mole. 1 kilocal was 4, so that's going to be, where are we? 437, 4, 1600, so 1,600,000 joules per mole, or 1,600 kilojoules per mole. Let's take that away. Back to our beginning. Clean up. Comprehensive mechanics. Okay. Calculate strain energy. And without doing any clicking or magical button presses, we get the total energy, 161.0175 kilocalories per mole, and then the breakdown of energy by components. So as I was mentioning a little while ago, the bond stretch, the angle bend, stretch bend, OP bend. Comment below, I have no idea. Torsional strain and van der Waals contribution, adding to the total energy of that molecule. I did find a nice thing from the University of, was it Berkeley? Yes, University of Berkeley. Okay, so in terms of these parameters, which you get from WebMO, we get bond stretch, angle bend, torsional bend, van der Waals. They've also got Coulombic interactions, which is, I assume, the electrostatic attraction between neighbouring atoms in a molecule. Then this is the total, and this is where I've got this idea from. So the molecular mechanics is a way of calculating the relative energies of molecules using classical Newtonian mechanics. It works well for a wide range, and you can see that the total energy, this is actually the potential energy of a molecule, can be modelled using 5 simple terms. So those simple terms are the simple terms which are here. Okay. So these terms that we get from WebMO are explained by this idea. Bond stretch, we have a simple Morse curve here, a Morse potential curve. This has got a Leonard-Jones potential. I never knew that. Okay, the Leonard-Jones potential. But what we're doing is we are moving, we are oscillating 2 atoms in a molecule until they're at perfect separation. Perfect separation, minimum energy. Okay, as it gets closer and closer together, the energy increases. Further and further apart, the energy is going to increase as well, until such a point as which the molecule will break apart, and that's going to be the dissociation energy. Okay, so bond stretch, this is the equilibrium bond length, and R is some value away from the equilibrium position. So the bond stretch is a measure of the distance between here, the minimum energy position, and any position beyond the minimum energy. That's the bond stretch measure. Angle bend and torsional energy. Torsional energy, this is where, let's say, at its simplest, you've got a molecule of ethane. I wish I brought a molecule of ethane with me. You've got the 2 methyl groups at each end. If those 2 methyl groups are perfectly lined up and the hydrogens on each side of that carbon-carbon bond are completely together, they're going to interact and give us a high energy on the potential energy plot here. So this is spinning around, this is spinning around. If they interact, the energy will go up. If they are apart, they will go down. So if it's eclipsed, they are together, high energy. If they are opposite or gauche, they will go down. So the torsional energy, which we get from WebMO, is going to be that energy which is here. So when those 2 atoms are interacting, what is the contribution of that level of energy? It's fabulous stuff, right? Gets me excited anyway. And then we go on, we have angle bend and stretch bend, and if we go back to our chart here, so we have van der Waals. Van der Waals interactions are treated with simple exponential function, are they? Which is the attraction and repulsion of neutral atoms. Okay, you all know the van der Waals definition, the energy generated by the instantaneous interaction between neighbouring atoms. Okay, words to that effect. So here's the summary. I've linked this hopefully on the, linked it here, meaning of terms on the little sheet, which I'll share at the bottom of this video. Clearly, I need to free up some space. So we're generating all this data. Why are we generating this data? Because we want to do an internal assessment where we can look at these different types of data. So my independent variable, the thing that I'm changing, is my cyclical alkanes. My dependent variable, I've got 1, 2, 3, 4, 5, I've got 6. Well, I haven't really, have I? I've got the total energy, which is composed of 6 parts, which I can look at those parts which feed into that one dependent variable. Now that's pretty gold for internal assessment. We can do a quick calculation. Total energy, change it into kilojoules per mole. That's easily done. Kilocalories per mole to kilojoules per mole. 1 kilocal per mole is 4.184 kilojoules per mole. I can look at the bond length. Yes, I can get the bond length from ChemLibra texts or the data book, I suspect, or anywhere, but it's nice to have that in there. Now, the UHF Hartree energy. This would be a great IA, I think. Looking at the total energy from the Newtonian mechanics with the UHF energy. And the UHF energy is the energy from all the molecular orbital calculations. So this is quantum mechanical, this is classical mechanical. And look at the difference. The difference is enormous. Okay, so I will just change the text here back to black. I just did that for the purposes of this video. So 167 is 701 kilojoules per mole. Bond length stays the same. The UHF in Hartree units, but 1 Hartree is 2,625.5 kilojoules per mole. So the UHF, the molecular orbital energy, is 307,000 kilojoules per mole. 307,183.5 if you want to be pedantic, kilojoules per mole. 307,000 compared to 167 is a massive amount of difference. Is that difference just to do with the molecular orbital contribution? And what do we mean by the molecular orbital contribution? Unfortunately, that's what we mean by the molecular orbital contribution. Because what we're doing is we're doing an unrestricted Hartree-Fock, and I'm pronounced that very correctly, equation, which sums the contributions of the molecular orbitals. Now look at the maths there. If you're an advanced higher level mathematician, knock yourself out. Have a good go at that. That will keep you occupied, I suspect, for at least the 10 hours which are allotted for the IA. What do I take away from this? I take away from this, there was a nice little diagram. There it is. Okay. So what we're doing is we're looking at the energetic contribution of the upspin, downspin, pi orbitals, and sigma orbitals contribution to the molecule. The bigger it gets, the more there are. That's as deep as I went on that one. Okay. So how do we get that? Okay, I have now transcribed my bond stretch, angle bend, stretch bend, torsional bend, van der Waals forces into my little spreadsheet here. And I will just change those back to the correct colour. So there we go. Now I can see. So cyclopropane is 60 degrees, as we would expect. That's good. These are the 1, 2, 3, 4, 5 contributions to the total energy of the molecule. I've changed that to kilojoules per mole. Pretty good data processing. I've got the length, throw that in there just for a laugh as well, and the UHF energy, which I've converted to kilojoules per mole. A bit more data processing. So how do I get the UHF energy? Okay, so here at the bottom of the screen, there's a little blue arrow. Hit the blue arrow. GAMES is the search engine, the computational engine we want to be doing. We are doing computational chemistry here. We want UHF. This is the Hartree-Fock thing. It's linked on the spreadsheet. Have a look. If you understand it, please send me an email in layman's terms and I'll happily listen to you. We want molecular energy, and we're going to send that to be calculated here. Is it having a busy morning this morning? Yes, as always. This is people are sending every couple of seconds something to this poor computer. I don't know where it is. I suspect it's in Iceland somewhere and it's just churning away in some fjord. There we go. We're done. So there's my C3H6. That will pop up in this screen. That's great. All looks the same until you go down. And then at the bottom here, you get the UHF energy in Hartree units. So you can just copy and paste that into here, which I've already done before. and converted it into kilojoules per mole using this equation here. So why is this useful? It's useful if you're at the point now where you're desperate for a research question or an IA. There's an independent variable. You don't need to look at the cycloalkanes. You can look at the cyclical alkenes. You could look at the carboxylic acids, acyl chlorides, esters. The list is endless of what you could look at and what happens as you increase the size of the ring. Or you could stay with one molecule, don't forget, and you can look at the, you can go and change the actual bond angle for different molecules just by clicking on the molecule. I'll rebuild my cyclopropane. What did I say about being over energetic with your clicking, Mr. Midgley? There we go. Thank you. Rebuild your cyclopropane. There it is. Clean it up. Idealize mechanics. Hit my clicking tool. SP3. Bond length. Bond angle. Adjust. Now I can adjust the bond angle. I'm going to here. Change it to anything that I want. 1 degree. What happens? Let's have a look at that. What's happened there? Oh my gosh. It looks as though we have a 1, 2, 3, 4, 5 pentavalent carbon there. We don't, because we changed it to 1 degree. But what's the effect on the energy? That's now 5,000 kilocalories per mole, which is about, was that 4 roughly? Yes, that's 20,000 kilojoules per mole. That's just ridiculous. But you can look at changing the bond length, the bond angle, and looking at the effect on the overall energy of the molecule. In terms of your research, you can do more research than I've done. You can use these links here, and there are loads of university websites with these things on. How is this calculated? This, and this. What are the calculations? Your data processing is going to be off the charts. That's going to be fantastic. You're going to find relationships in here which have not been covered by the IB syllabus. There's personal engagement, there's exploration. Analysis, what you're going to do for uncertainties, last decimal place, change it to percentage, off you go. And then you're looking at the difference between Newtonian mechanics and molecular orbital quantum mechanical calculations. If that's not destined for a 24, I don't know what is. Okay, I started off by saying take care, be careful. It's taken hours and hours and hours to get to even this basic proficient, I won't even say I'm proficient, just very basic point in my grasp of WebMO. And I still have not as yet worked out how to add lone pairs of electrons. Okay, so I have no idea what happened just there. There we go. There's the topic for the next video. Thanks very much for watching. Hope you enjoyed that as much as I do. Again, this sheet will be at the bottom of the video for what it's worth, and you can continue this and perhaps go 1, 2, 3, 4, 5 up to hept. Maybe you can do 10. It took about an hour to make this. Okay, with the background research, data processing, conclusion evaluation, you should be approaching 10 hours for this as an idea for an internal assessment. Okay, keep working, keep playing with it. Have a great day. Smash that subscribe button. Thank you very much indeed for watching. Bye-bye.